आपको किताबें पढ़ते हैं?
Yes, yes, sir.
लिटरेचर पढ़ते हैं?
लिटरेचर सोच से हट के वो भी पढ़ते हैं, सोच के पढ़ते हैं.
एक ऑथर है युवल नोहा हरारी, उसकी 4 किताबें पढ़ी हैं. देखिए, सेपियंस, brief history of human race. Sapiens. I am sapiens. Second is Homo Deus, Deus. He's a fascinating author. Because I read a lot of books also. I have 5,000 books in my home. अगर आप लोग जब चाहें आए हमारे घर की लाइब्रेरी में, there's many books in the age.
हम आ सकते हैं.
Sure. And second book is called Homo Deus, a brief history of future. Actually, history of future. That book, you will let me write this. And the reason I'm saying this, if you would read one book, okay, name of the author. And if you want, I can bring that book for you. And you can then read it. The third book is called 21 Lessons for the 21st Century. 21 Lessons for the 21st Century. This is the third book. And the fourth book, which came only last year, was Nexus. And that is the history of information. These are fascinating books. If you read one book, Sapiens, completely, you get 2 PhDs.
You have time to read book?
Huh?
Have you time to read all?
I do really read a lot of books. I in my cars, wherever I am, I have books. When I travel, I have books. In my rooms, wherever I stay, I have books. So we have a lot of books here. So reading books is just absolutely one important thing. It just opens up to you to the world. And remember that when you study chemistry or molecular biology or whatever, it's just a very small portion of knowledge. Life is much bigger. You need to connect yourself to the world. And so books are extremely important. Must always. And in next 2 weeks, I'm planning to start I will start from Socrates, Socrates,
Yes.
Greek philosopher, and I will start from dialectical discourse. There are several things: dialogues, debate, discussion. Then Romans and ancient Greeks, they used to have a very, very different way of communicating, and that used to call dialectical discourse. इसके अंदर का पढ़ी का क्या होता है? Dialectical discourse, so dialectical discussions. Dialectical, कहते हैं, the best translation of this is called Mantati Istadlal. Manta, logic. Istadlal means it's Dalil. You know Dalil?
Yes.
Yes, Mantaqlid. Okay, so if you learn how to communicate, and you know, we always discuss to win the discussion, and in the process we lose. When you win a debate, you actually lose because you're so rigid that you're trying to impose your point of view and never learn. Okay, so what Greek philosophers used to do, they used to discuss mantaqi istidlal, this dialectical discourse, with dalil, with mantaq, and they were just so absolutely open-minded. If they were convinced, they used to say, yes, we were wrong, and we accept it. If they don't agree, they agree to disagree and respectfully leave. And there was a knowledge exchange. You don't debate for winning, you discuss for learning. Okay? And so this is what I'm going to discuss with you in philosophy of science. When I discuss with people, I never debate. Okay? I have in my life, I never tried to win an argument. Because I know if I win the argument, I lose the argument because I would lose the opportunity of learning from someone who is unlimited. You know? So this is what two important things. You would read at least one book of Yuval Noah Harari or Hariri, right? He's an Israeli historian. Of course, I don't agree with his political views, but this book, he's a phenomenal writer. Never seen a writer of that impact. And second is that when you discuss with each other, don't debate. You all use Greek method of learning, which is dialectical discourse. Discuss to learn, not to win. Okay. Anyway, so today is fortunately, unfortunately, our last discussion, and this is what I am inviting you in Islamabad. Okay, so you can take a picture. You can have the registrations. Everything is written on it. Okay. Your whole visit would be sponsored, and of course, subject to the approval of your supervisors, we would take you to Islamabad for some of the finest people will teach you. They and that is going to be more on. You see, I think I was actually in the way when I was coming from. I'm just coming from Lahore. I woke up at 4 o'clock in the morning and went to the airport, took a flight, came to Lahore. And last evening, I was in Islamabad, so Islamabad to Lahore, I reached at 6 o'clock. Anyways, and day after tomorrow, I'm leaving for Saudi Arabia. Anyway, so what I was thinking.
Sir, I would like to add that yesterday, last night, sir got the award from Hamdard. Very exciting.
Yeah, that's and I think is more interested not in award, but that little check which came with it. So I think we should really have special classes on these beautiful new technique called concatenated techniques. Concatenated. This is a new type of NMR emerging, which Pratya is expert. These are the technique which is called multiplex, called constructive interference. These are techniques which you actually combine. Think of HSQC, This is HSQC. This is HSQC spectrum. F1, carbon chemical shift. F2, proton chemical shifts. You relate proton with carbon. See, right? On the floor, you have cross peaks. You have cross peaks which representing direct connectivity of carbon with proton. And then you add another dimension, F3. Okay? And that F3 is toxic. So the proton, which is connected to carbon, is also correlating with every proton in the spin system. So this is a mix of two techniques called HSQC toxic. And there are many combinations, HSQC, nosy, there are HMBC nosy and others. They're called concatenated technique, concatenated. So this is amazing. And we have written that in our book. We were the first one who, of course, we have not invented that. We just I think we should discuss sometime with them all these beautiful techniques which but okay, so having said that, this is what we were discussing, HMQC or HSQC. They are primarily essentially the same technique. HSQC is a bit modern, new, better, improved resolution is better. HMQC is little historical, which was developed in 1979. People start using it in 1986, and this is a heteronuclear one bond coupling. Heteronuclear means proton carbon or proton nitrogen. They're interested more in nitrogen, so they're like, which proton is connected to whose nitrogen. So these cross peaks represent connectivity of proton and carbon to get direct information about which proton is connected to which.
According to this, you didn't explain how to do that according to the first quiz. How to do that in the frame, rotation frame. How we can do that? Naked bulbs done and not.
You want that? Okay, so the man wants torture. Let me start this. This is the technique. Okay, so this is proton, and this is heteronuclear carbon or right? The classical traditional polarization transfer was proton to carbon. Done? Finished? That's what you have studied. You have studied transfer of polarization from proton to carbon, and you're detecting carbon. T2 is detection. Okay. This is classical inverse. Carbon to proton. Inverse.
The same way?
Same way?
I mean, first, the 90 bulb, then we.
It's very logical for us to understand that when we have proton carbon cross polarization transfer, you keep carbon on the XY plane because you're detecting it. If you want that to be reversed, then proton has to be an XY plane. It's obvious. You understand? So the reverse. This is the reason why it's called inverse polarization transfer. So this is the traditional polarization transfer which we have studied. Okay, same pulse sequence inept. And this is the inept in reverse sense. Exactly reverse. So what do you do with proton? In that case, you do it with carbon. And this is the modern inverse technique. What you do, you transfer from proton to carbon and then carbon to. So what do you detect? Proton, right? But the beauty of this is that you have first increase the sensitivity by proton carbon polarization, right? You have Adil has given money to Mahmood for reverse algebra, right? So already carbon is strengthened. From that strong carbon, you reverse it to proton. You understand the philosophy? This is traditional polarization transfer, proton to carbon. Okay? Carbon gets strengthened because insensitive nuclei get polarization from sensitive nuclei or nitrogen. Always remember when I say carbon, can be nitrogen also, effectively used. The traditional inverse way is that you transfer polarization from carbon or nitrogen to proton. Fine, you get information, you is a proton detected, but not so good, because proton will weaken, carbon will weaken the signal of proton. Exactly in the same philosophy as proton strengthen the signal of carbon, the carbon will weaken that, But if you do this trick, first you strengthen carbon from here to here, like this, and then from carbon to proton. So you detect proton, but you have an added advantage. You have added advantage that you have already done a forward polarization and then a reverse polarization. So first strengthen the carbon, and then from strong carbon you transfer the polarization to proton, and you detect the proton. This is phenomenal. Think of people who were so zahin, intelligent, that they were thinking in a way of like this. Yes, sir.
Only a couple of things he will respond to this pulse. That means most bonds we cannot stay. We have 99 abundance of carbon 12, but only the carbon 13 will respond. Okay.
So carbon 13.
Yeah.
This is the only isotope of carbon which you can read.
But he will show us all the bonds, all the carbon in the.
No. Carbon 12, you can only see that in dream, and not in NMR. Okay? Because you know the reason. I remember this beautiful quote of Dr. Abdul Kalam, and write it, Abdul. Dr. Abdul Kalam says that dream. Dr. Abdul Kalam was the president of India, and he was the founder of India's nuclear program. And he said, dream is not what you see when you're sleeping. Okay? Dream is the one which keep you awake. ख्वाब वो नहीं होते जो आप सोते हुए देखते हैं. ख्वाब होते हैं जो आपको हमेशा जगाए रखते हैं. फर्क आता है. It's okay. Why? Sorry, I just off track. This is unfortunately when you get old, you off track. Okay. So this is the philosophy of modern inverse NMR spectroscopy. Carbon 13 is the only isotope of carbon which is visible, but it's very weak. It is weak because of 4 accounts. Natural abundance, very low. Dynamic ratio, is a poor magnet, and I don't know what else. So you're trying to, yeah. So what you're trying to do is to enhance the sensitivity of carbon, right? That is by polarization carbon. But an absolutely different experiment was developed when they said, we don't want to detect carbon that would always be weak, no matter what you do. you detect proton and you detect carbon indirectly through protons. As I showed you that if you have a mirror, magnifier mirror, and then you see yourself in the mirror, and people see yourself in mirror, they see you, but they actually see the mirror. So they see the proton and the effect of Samayako. We have a very distinguished new student with us now, Dr. Ilma. How are you? She told her mother that he's a good teacher. You think that I can teach? Maybe. Okay, so this is the inverse model. This is the inverse model. So today, all the NMR, all HMBC, HMQC spectrums are inverse, modern inverse, in which you have first polarization transfer. But you don't need to worry about it. You just need to understand that this is proton detected. On F1, is a frequency one domain, which you have a proton chemical shift. And in F2, you have a carbon chemical shift. Remember that these spectra are not really generated by two dimensions, they are generated separately and then pasted. Okay, just for your understanding. Actually, you don't need that, You can just always calculate. You need a horizontal line and a vertical line. Okay.
Yes. Sir, as per your instruction, like a couple of years back, in our NMR labs, we are only doing whoever write HSQC, or we just do depth HSQC. So that
This is depth HSQC. Polarization inert. This one.
Depth HSQC in which we can identify.
Oh, okay. That concatenated. That's a concatenated technique. Depth. We don't, not at this stage. It was super confusing me.
And we get older. That is bad.
You're stuck between four people. Okay. So this is an amazingly beautiful technique. Every contour in it, every cross peak is representing a proton-carbon coupling, single bond. Right? Now, think of it. How would you connect? You have a structure. I write a structure. I don't know whether you can see this because these all are not so good, but think of it. Let me draw a hypothetical. I'm not sure it's not hypothetical. I'm sure that many such structures exist. Okay. Management system.
One.
So far, you only get this. Yeah, only this. Disconnected, fragmented, So you have, you got it, for instance, this you get it through COSY, right? Also HSQC, proton carbon, right? You have this, maybe you can put X here, because this means that these are the fragments. There are three fragments. How would you connect them? You got it through COSY, you got it through TOPSY, you got it through HSQC. Well, how would you connect them? That's the problem. And this was a problem when scientists started thinking of not heteronuclear direct coupling, but heteronuclear long range coupling, multiple coupling. So a new technique was developed in which 1, 2, 1, 3, and occasionally 1, 4 couplings can also be seen. And this is called HMBC. HMBC, right? And this HMBC is, remember that direct proton carbon coupling is above 100 Hertz. Direct proton carbon coupling is about 120, 130, 140, occasionally about 150 also. 1-2 coupling, 1 proton after 2, coupling roughly in the range of about 8 or 10, and then 1-3 coupling is about 6. Now, you have all this, you have 3 fragments, 1, 2, and 3 fragment. 3 fragment. How would you connect it? And that's absolutely indispensable, 100% required. 100% zaruri cheez was developed, and it's called HMBC, heteronuclear multiple bond connectivity. Multiple bond. So the technique was developed in which direct one bond coupling of 100 Hertz were just eliminated, only the long range couplings. Now I'll show you what actually happened. In this spectrum, well, we have another color. Okay, in this spectrum, you should be able to see the coupling between and this. Okay, this is 1, 2, 3. Okay, you would be able to see the coupling of this proton with this carbon. Right? 1, 2, 3. You would be able to see the coupling of this proton with this carbon. 1, 2, 3. And if you have like this, what you need to do, you know exactly if this proton is coupling with this carbon, multiple bond, this must be connected. If you see that this proton is connected to this carbon, so show a correlation. This proton is showing up correlation with this carbon, cross peak. It is connected, right? And if you know that this proton is connected to this carbon, you connect it like this. And even those carbons, which you can never see in any spectrum, except C13. For instance, you will not be able to see this in HSQC because it has no proton, right? It has no proton. You'll not be able to see any topsy of this because it has no proton. You'll not be able to see any cozy of this because it has no proton. But you would be able to see okay? So you have this beautiful technique that you are able to identify even the quadratic carbons. How would you identify this quadratic carbon? In chemistry, it's called ipsos. You know, ipsos are substituted carbons. So, how would you identify this carbon? The chemical shift of this carbon. I can do it because I would be able to see this correlation of this quaternary carbon with this one, correlation of this carbon with this one, this one. And when I can do that, now three advantages. Number one, it helps you to connect the fragments. There is no other technique in the world in NMR which can help you to connect fragments, spin systems. This is the only technique which helps you to identify quadratic carbons, such as this one, such as this one, such as, and in certain cases, it also helps you in stereochemistry. HBC help you to do stereochemistry. Now, this is the technique which is based on a simple premise, nothing fancy. Essentially the same proton detected heteronuclear technique, like HSQC or HMQC. The only difference is that in the pulse system, they eliminate by using destructive interference the J1 coupling. Direct one coupling they eliminate. So you see only the long range coupling, 1, 2, and 1, 3. Occasionally 1, 4 also. In aromatic rings and methylation system, you can see 1, 4, but that's a different reason. So this is the only technique which help you to connect the fragments, and essentially the same experiment as HSQC and HMQC. Essentially proton detected, essentially tricky because proton to carbon and carbon to proton, right? But in this case, you do a trick. You minus J1 coupling. J1 coupling means direct proton carbon coupling, which is 100 Hertz. There are pulse sequences which are beyond this class discussion, because they introduce another delay and they minus it as a different domain. But they have somehow eliminate minus one CH1 one bond coupling. Okay, and what remain is these small little satellites of 7 Hertz or say 8 Hertz, which represent J2, J3, occasionally J4. J2 means 1, 2 coupling, proton, second carbon. 1, 3 means proton, carbon, carbon, another carbon. Okay, in conjugated system, you occasionally see C4 coupling also. So let me HBC is a phenomenal technique developed initially for carbohydrate, because carbohydrate, always remember, they are linked with each other through oxygen. If you have a disaccharide, how many spin systems in sucrose? 2. How would you connect them? Because in between there is oxygen, isn't it?
Yes, sir.
You get from one proton of one saccharide to carbon of another. So it was essentially developed for carbohydrate chemistry, but then now it is used, everybody is using it. And extremely interesting technique, almost essential. A lot of nitrogen work is being carried out in protein chemistry. They try to identify proton-nitrogen coupling long range. Okay, so they can connect. Think of amino acids. Protein is a chain of amino acids. Between there is a carbonyl group. And there is a different spin system, you know. You cannot connect them together because there is no unbroken chain. So you use HLBC, right? You have one proton, one carbon connect to NH, or NH connect to. So
If we have big molecular macro, and that we call them like polymer or like protein, we have thousands of molecular.
yeah, that is a very important question. Thank you. You know, in protein, they are literally. It's not as simple as you see here, and this is the reason I never tried to learn protein NMR spectroscopy. It was just too complex for my brain, and I left this to younger people. You know, you can have like 1,000 peaks, like this, or maybe 2,000 peaks. What big biopolymer, these huge peaks. But they know how to do that. You know? Number one, they have this concatenation technique. They have three-dimensional techniques. They can take some of the peaks onto the third dimension, right? They also use strains. You know, I don't know. She will explain to you. I don't understand much of it. They use restraints or constraints or restraints or whatever. Because remember that protein structures are not linear. The actual protein structure is three-dimensional. And this three-dimensional structure means that an amino acid which is quite far away can fold over onto the other. And what will help you? Nosy will help you. NOE will help you. So there are other techniques which are used, and they use all these. And they also have very fancy techniques which I don't know absolutely nothing, like proton, nitrogen, carbon, CNCAB, something. Huh? She once told me, I remember it.
But one of the example like HMCA,
Yeah, आपको समझ आ गया होगा आपको एक मिनट में समझ भी आ गया So there are many techniques which are designed for proteins, you know, but these are just very introductive. So they are not so fancy. They are not so. Okay, so this is what now what you do. You do exactly the same thing. Every peak is representing a proton-carbon correlation, not connectivity. There is a difference. Connectivity I would use when there is a direct connection. This is correlation between proton and a long-range carbon, or long-range ion. So each one of them, for instance, if you say, okay, this is this proton, C2 proton has long-range correlation with C10, right? Isn't it? It has also a long-range correlation with C7. 1, 2, 3, right? This has also a long-range correlation with C5. No problem. This is HMBC, right? HMBC, proton, carbon connectivity, long range. Okay. But cross peaks represent. It's so simple, you know. This is C4. If you assume that you have this is one spin, this is how many spin system it has? Two, right? But these spin systems are broken because of this oxygen, and there is carbon. So this is one spin system, and this is the other spin system. How would you connect that? Because you can see the correlation of this with this. Okay, you can see the correlation of, let's say, 6 with this. So these correlations, long-range correlations, help you to identify how they are linked, cemented together. How can you take these bricks and put them together? HMBC provides you that particular kind of information. This is HMBC, and amazingly simple. I mean, you just need to go to proton, look down, and you know which which proton has correlation with carbon. So, for instance, we said C10. C10. You know, there are two peaks. Remember this? These are isotopic. C10. Correlation of C10 with other C10. Okay. So there are two. And this one? C9. And this one? See? Now, for me, this is very important because this is the terminal carbon in my spin system, which I would like to connect. So C2, assume C2. Where is C2? C2 is correlating with C10, C9, C9 or C7, C7, so the C6, C7, and C2 also. Why C2 is coming as a doublet? Where is a doublet? Remember, CH going to be a doublet, right? Proton detected. This is a proton NMR. This is a proton NMR. Always remember, these are not carbon NMR. These are proton NMR. So you and so HMBC technique was developed, and okay, then we move forward, and we come to the last topic of our discussion. Sadly, so we really wanted this class to go for another 30 years or so, but I made you a structure, and I honestly don't know how would you call that structure as a structure. If there is a straight line here, there is a stereochemistry here.
Yes, sir.
It's behind.
There is a stereochemistry here also. How would you know? How do you know? Behind or above?
Dash.
No, but how would you elucidate that? No, it's SP3, but that can be up also. Right? So only connectivity is not important. Stereochemistry is also important.
Yeah.
The structure is always stereochemistry. For them, for protein structure biologists, same 20 amino acids, thousands of proteins. Why they are different? Because they are different from their sequence, but also most important, they are different because of their three-dimensional structures. And what three-dimensional structure means that one protein, which is 5 carbon away, fold over to another protein. How would you determine that? So it means that there is a need of a technique which can see coupling in space, not directly scalar coupling, but a dipolar coupling. Okay. And this fascinating technique was developed by Overhauser Overhaza was a scientist. I forget the name of full name of Overhaza. Somebody can Google that. Yes. HSQC is, I mean, of course, there can be artifact, you know, there could be experimental error because sometimes these pulse sequences are not really perfectly. In HMBC, you sometimes get one coupling, one carbon coupling, super confusing. But generally, in HSQC, you would have only one carbon. And in HMBC, you would have 1,2, 1,3 coupling, occasionally 1,4. Right? In conjugated system is a different reason altogether.
Sir, it's Albert Warner Overhaus.
Albert Warner Overhauser was the name of the person who discovered this fascinating technique. And this is the reason why always you write it O as a capital, because it's a name. Right? So whenever you write nuclear Overhauser, O would always be in capital, even in abbreviation. Okay? Because this is the name of the person. So Albert Overhauser was the first one who discovered that there is possibility of seeing some correlation with protons which are close in space. You know, they are not directly coupled to each other. They don't have a scalar coupling, but they have proximity in space. There are many molecules in organic chemistry and others where you know that the rings and others fold over, the chains fold over. There are protons which are close to each other, and that help you to build this frequency. So NOE, nuclear Overhauser effect, was developed, and this is dipole interaction. It's not J coupling. It's not scalar coupling, through bond coupling. It is through space coupling. In the space of the two protons are close to each other, if two protons are close to each other, they would have some influence. And you know, he got this understanding from a very simple experiment. Imagine this is a bar magnet. One proton. Remember, a proton is a magnet also. Always remember that proton is a magnet. And this is another magnet, right? It has south pole and north pole. This is called dipole. It has north pole and south pole also, dipole. If I bring them in the space together, just do this experiment. If you try to bring north closer to north, what will happen? If you try to bring north to south, and vice versa, it means he said, how come on the face of the earth, if these two magnets, if they are close in space, it means that they are close to each other. It's pure chemistry. If they're close to each other, they would have effect on each other. Yeah. Where are the magnets? Right? Simple thing, you know. Simplicity is the essence of science. The simplest thinking we have, not linear thinking. There is a difference between linear thinking and simple thinking. Simplest thinking you have, more elegant you are in your way of understanding. So Newton, as I said, this apple fall on his head. And as I said, there were millions of people who had this apple fallen on their head as well. He had a very simple analogy. Gravitational theory was well known before this discovery. What he has done was a very simple thing, that if Earth has a gravitation force, then the other planets have a gravitational force also. And he said, how come these planets are moving all around each other and there is a moon who is circulating? What keeps moon circulating around the Earth is gravitational force. So he expanded that narrow gravitational force of the Earth to a universal gravitational theory. Simplicity. So, right? Okay? Two bar magnets, they will influence each other. You are convinced? And this is called dipole-dipole coupling, or a dipole-dipole correlation, or through space correlation. Through space correlation. And that is in the respect of the person over Hausa, nuclear, because these are nuclear, protons, carbon, whatever. And over Hausa was the first one to discover the effect of nuclear spin to the other nuclear spin in space without any bond with each other was called nuclear Overhauser effect. Extremely important truth. Remember, in this structure, I made this structure wrong. You have never told me. This can't be like this. It can be up or right. So this structure would never be accepted if I send this publication for publication. They will reject it right away. Because in chemistry, the structure is always three-dimensional. It's not two-dimensional. So I have to determine the stereochemistry of this. Either it's up or down. Okay? For that I need to have NOE. If I make this a bit more complicated, and CH3 here. How many chiral centers? How many chiral centers? 2. So how many possibilities exist? Both of them down? Both of them up? One up, one down, this up, this down. So what is the structure? How would you know the structure? Isn't it?
Yes.
It's a puzzle. If you got the connectivity, you got the structure right, but it's not good to go because you have to have a technique which helps you to determine the proximity, right? And for that, NOE was developed. So it is through space interactions. Through space interactions of nuclear spins, and typically employed at the last stage of structural investigation, because when you would have connectivity structure, only then you will look for stereochemistry. You will not be able to do stereochemistry before you don't know the structure. Okay? Only when I have a structure like this, then I would need NOE. So right at the end of structural elucidation, and they too, the protein chemists also, they get a lot of connectivity, proton, carbon, etc., etc. And then right at the end, when they're constructing three-dimensional structure, then they see the NOE, thousands of peaks, weak NOEs, strong NOEs, and all that. Let me ask you a question. These two magnets, depending on their power, assume that they are just very small, tiny little twice magnet. If I put them far away, will they affect each other? So this is dependent on distance. Okay, so overall they determine that the weakest NOE, the first time you can see when it's close to 6 angstrom. Right? They go closer to each other, you get stronger effect. You go farther away, so you can even measure the distance between two protons, depending on the intensity of NOE. NOE between two nuclear spins, which are just 1 angstrom away, is going to be stronger. 2 stronger, still stronger. 5 weaker, 6 weaker, 7 no NOE. So what the no NOE means? They're not close to each other. So you see, it's all logic. This is all logic which has constructed this beautiful idea of distance-based dipole-dipole coupling. And this provides information about three-dimensional molecular geometry. Because remember, the structure is three-dimensional always. And again, depend on internuclear distance. Separation means distance, right? You agree? Interpretation of NOE measurement requires extreme care. I'll tell you why it is extremely care. There are two different types of NOEs. You should not really worry about. There's one-dimensional steady state and the two-dimensional noisy transit array. So internuclear distance 6 angstrom or less, then you will be able to see some effect. And there's also an extremely interesting thing which I would ask you. For instance, if you have this two magnets, two proton, close to each other, and somehow you're just impatient, not so good, or just in the hand of a child, he's just moving like this, right? This would have more correlation, or the one which are slower. The effect, where would be effect? It means if there is a tumbling, which is called effective correlation time. Tumbling, strong tumbling, then you would have weaker energies. When there is a slow tumbling, you would have different kind of energies. And also the angle, right? Angles are important. As I said, north to north, south to south, right? So there's so many things which are important in NOE, and this is the reason why. Now, question was, how would you measure it? Like all NMR theories, the question was, the theory was so simple. How would you measure the effect of one proton on the other in terms of through space coupling? And for that, a very neat experiment was designed, which is again very close to the correlation experiment, polarization experiment. I don't know whether we have this somewhere. Okay, this one. Okay, so you have two protons. They're not directly coupled. Okay, but they are close to each other. So they're affecting each other, right? And depending on their angles, they can be in 4 different stages. Alpha, 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 beta, 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 right? But they're not scalarly coupled. They are through space. They're affecting each other because their proximity force them to have effect because these are two magnets close to each other in space. Okay. And always in NMR spectroscopy, the transition are W1. One of the spin change and not both spin changes. This is called single correlations, single transitions. So forget this one. इसको भूल जाएगा. These two things are affecting each other in space, and they are in 4 different stages. Like this, like this, like this, like this, 4 different stages. You understand? So now in theory, you can have one change. You can have the other change, but you can have 4 different type of changes called single transitions. From beta to one transition. one transition, one transition, one transition. Understand? Only one of them transition. And remember, this is the relaxation. This is the highest energy state, and this is the lowest energy state. Remember the B naught, magnetic field, right? So, so simple, right? But you can't measure it.
What are proton now? How you can prove only one of them?
No, but protons exist in how many forms? In magnetic field. No, how many forms? How many forms? One proton can.
Alpha or beta?
Alpha or beta. Meaning if there are two protons in proximity, four possibilities.
But if you give one of them change from alpha to beta.
No. See, if they relax back from beta, they will relax back in a single transition. This is because proton system. I remember I told you that NMR is a weak force. Is a physics of weak forces. The energy release is very difficult. It's such a tiny energy that one of the most difficult things to understand in NMR spectroscopy is to where this energy goes and how is this energy goes. There are chapters written about it. Okay, so the easiest thing is that one flip, the other flip, and actually they have these four stages. Now, what Overhauser said, I would saturate This is my S, this is my I. I label two protons saturate. S means I will saturate that saturate with what? Pani, Fort, radio frequency, right? And the other is I. Interesting. I am interested in learning about it. If S and I close by, S would have some effect on I, and vice versa. If there is no effect of S on I, it means they're far away. Okay? So if I saturate S with lots of radio frequency, other than normal radio frequency pulse, this is a second pulse which I give to S, my S proton. It becomes an absolutely abnormal system. The system is just full of energy now. Full of energy because other than normal pulses, I have given this absolute saturation, so selective saturation to S. I saturated on the chemical shift of S. I just give this S more radio frequency. This led to a complete disturbance of the system. This system will become an absolutely abnormal system where S has so much energy that it cannot release it by using single transition relaxation. Remember, this is excitation, this is relaxation. Why is two arrows? Excitation and relaxation. That this system will not be able to release the energy by using allowed relaxation mechanisms. Overhauser was the first one who measured that when such system is created with supersaturated S, there is another mechanism trigger which is called forbidden relaxation. Forbidden relaxation. Forbidden means not allowed. Generally, it's not allowed, it's not seen in NMR. only when you give exactly the same way. If you really pressurize each other, right, and not so nice to each other, what will happen? You will be abnormal, right? Slap on your face. Exactly the same way, forbidden things start happening. Okay, and that forbidden thing is double quantum realization. All of a sudden, realization will start adopting. Two of them, both beta will become alpha, because the system has to restore thermal equilibrium. Okay, and that eventually lead to nuclear overhaul effect. This is a competition between 5 different types of relaxation. 4 normal and 1 abnormal. अभी इसको ज़्यादा उस पर तवज्जो न दें, और चीज़ है, tell you later. Right? Competition. And this is the reason why NO is a very complex technique. Complex so much that when you go and say that I would like to have my NOE run on NMR, they will ask you to degas 100% filter, take out all gas bubbles from your sample. They have called purging. They use argon to remove all different gases also, because if it is all the game of relaxation, then any particle of air or any solid particle will destroy your experiment. You get nothing, right? You're trying to measure a very rare phenomenon which happens only in supersaturated systems. And in this case, it's quite difficult. Okay, so Aditya, shall we go into this or not? No? Okay, we'll go in it. I need somebody's help. Where is other Yamani? Yeah. He's my problem solver. So this is the normal NMR. There are 2 protons not coupled to each other, that you don't see any splitting. Remember, it is not scalarly coupled. They are only close to space. And when they are close to space, they exist alpha alpha, beta alpha, beta beta, right? There should be a population also, right? So it is n plus delta. This is n, this is n, and this is n minus. What is the difference between them? Minus. The population difference between this. Chef, help me.
This is minus delta. And this
Okay.
minus delta.
Okay. What about this?
It's minus delta.
And above?
And above 2 delta.
No. This one.
N minus delta.
And this?
Minus delta.
There's always delta, isn't it? No effect to each other. So, no effect. You can't measure it. Now, what you do, you saturate S. When you saturate S, you create a system in which all of a sudden this double quantum relaxation trigger, which is forbidden, not allowed. Now tell me about the difference in population. Yeah. Okay. this,
bigger than this.
this, and this. You see, the proton which you saturated will not be visible. You know this, right? When you saturate anything, they're not on XY plane. You can't detect it. But because of that saturation, the W2 triggered. And because of W2, the intensity of I has increased. Isn't it? And Yahya will explain to you. I'm going home. No, why not? Okay, you explain again. What is the population difference? In S, what is the population difference between S? What was the population difference between the normal system? Delta, right? This is the reason that you see. And what was the population difference between I? I is my interesting nucleus. I'm interested in that, and that's why I call I. S is my saturated.
How to saturate it? Using specially
Oh yeah, very good question. This is very much possible. You select the chemical shift. You give a very specific radio frequency of that frequency and saturate. There's the reason it's called selective saturation. Yes. And you can do it, in NMR. Now, what is this population difference in this case?
The population between this 0 and in this case bigger than delta.
It means what happened? S is gone,
And the I
S is gone, and I is enhanced. And that tells you that S is close to I. If S is not close to I, there will be no change in intensity. It's called nuclear Overhauser enhancement. It's also called NOE. The second name of NOE is nuclear Overhauser enhancement. Okay. This is the enhanced signal, right? Enhanced signals. What happened in large proteins with extremely slow tumbling? W doesn't, and I'm going through a dangerous water. I'm sorry about it, but I really I not miss this. When you have large proteins, like the one which Dr. Atia is handling, large size proteins, this W2 doesn't work.
Right.
Only I'll tell you, W1 work. When W1 work, what will happen?
this will be the difference between this. And it will be smaller than delta.
It means it's called negative NOE. The signal, instead of increasing, it decreases. So you can have positive NOE in the small molecules, or you have negative NOE. And people use it for amazing purposes. They record the NMR of a small molecule, they get positive NOE. They take that molecule, put it in large proteins irreversibly, and record the NOE of that same molecule again. It will become negative. So amazing science that you can. Now I'm sure that and we were to repeat it at some stage also. This is the same in terms of dots. Okay, this is how many dots? How many dots? How many dots? 0. The difference between this, difference between this, difference between this, sorry, difference between this, Difference between this 2, right? Same. You saturate S, and what will happen? Difference between this, difference between this, difference between this, difference between this. Okay. So you have enhanced system. Okay, so there is one more spectrum. There is one more for you to explain. Okay, now this is a large molecule. Okay, and there are so many stereochemistries. This one, this one, this one, this one. How many chiral centers? 4 chiral centers. You know, theoretically, nitrogen is also chiral center, isn't it? You agree with me or not? Is a chiral center or not? Or you don't see that? Why? This little 2 protons flip-flop, go down, go up, and you don't see the chirality of nitrogen. Nitrogen is true and honest chiral center. When you convert nitrogen into pottery salt, it's a superb chiral center. Always remember, phosphor is a chiral center. Sulfur, so you don't ever think that only the carbon is a chiral center. You know, they can all be chiral centers. Anyway, so there are 2 chiral centers, right? 2 more, 4 chiral centers. How many combinations this can have? It's a nightmare. No, Chef, it can be more than that. How many?
64.
64. Now, out of 64, only 1 is correct. How would you know? By NOE. Now, how would you do that? Saturate this one. See the effect on it. If it is on the same side, you see the effect. If they are on the different side, no effect. Similarly, saturate this one. You see the effect on I, they are on the same side. If there is no effect, it means they are on different side. Now you have reduced 64 to how many? They have to be on 2 different sides. There is no NOE observed. How many now combination you have? They are different, you know, because they are not showing NOE with each other. So one is up, one is down. The other also, one is up, one is down. They are on 2 different faces. How many combinations you have? Okay, why 32?
How?
Hmm? I don't know actually how many combination you would have. 1 up, 1 down, right? It can be like this, right? The other 1 up, no, 2 up is no possibility. I tell you that no energy is observed. Now we are struggling with another kind of problem that you have now a limited number of stereoisomers to be decided. You use again NOE. Now you saturate this one. And we say, see the effect on this. Okay? If this is on the same side, you further reduce the possibility. So you keep doing it, you know, it's called one dimensional steady state. And these are my favorite molecules. How many combinations you can have? In this case.
Oh. Oh. Oh.
Yeah, 4. Right? How would you know that proton are close to proton and not the vice versa? You have to use the NOE. If saturate one, you see the effect on another. In this case, how many possibilities? Well, these methods are essentially the same, so it's not so interesting. To be honest, I'm not happy with this. In this case, your structure is ready. It's not final. It can be trans or cis, right? Z or A. How would you discover that? If you see the effect between this proton and CH2, they are on the same side, cis, right? And
We have 2 protons here. How will we access them?
that I don't know, to be honest. Anyway, so this is a heavy atom, right? This is also heavier. This is a cis, right? You can have a reverse of it. You can have like this. This is the other. इनको क्या कहते हैं जिसमें डबल बॉन्ड से डिफरेंट होता है? Geometric isomer? No. There are diastereomers also, but that's dramatically different. But there are diastereomers also. Remember that, but they're different. Now, there are 2 combinations. The NOE will tell you which one exists. Because you need to kind of a fishing. First let's try this H. Saturate S and see the effect. Where is the effect? If you see the effect here, it means they're on the same side. Right? And if you don't see the effect on this one, then probably this situation exists. Right? In that case, you go and conduct another experiment. You irradiate this CH2, okay, and you see the effect on this CH2. It means that they are cis. So it's right a difference, yes.
I have more than there are same type of groups than that. So I do the experiment every time for just.
Very good experiment. Very good question. If we have so many chiral centers, and if you need to do this experiment one by one, saturating one, this was my age when I was doing it. Life was so difficult at that time. But enjoy it.
How do take Lebanese?
You don't like it? What can I do?
It's very similar.
Okay, so
Now,
listen. So now this technique is 2-dimensional, nosy, in which you don't need to irradiate one by one. You got all cross peaks in one spectrum. It's called transient. Let's see this also. Isn't it an interesting example? Indo and exo, same molecule. How would you identify that your molecule is indo or exo? Because as a chemist, remember I told you the chemist have 3 attributes. You can never be called as a chemist if you do not really know 3 attributes. What are these? Okay. You are not a chemist. Number 1, capacity to isolate one compound from a mixture. If you cannot do that, you're not a chemist. Second, capacity to identify the structure of an unknown molecule. If you cannot do that, you're not a chemist. Capacity to change the structure of a molecule as you wish. Derivatization. if you have these three attributes, only then you can qualify to be a chemist. Plus, finish, act. If you lack any of these attributes, for me, you're a half chemist, quarter chemist, 1/3 chemist, 0.1% chemist. How many attributes? Number one, from, chemistry is such an essence. You should be able to isolate one compound from hundreds of the compounds. Mixture. It can be 100, it can be 2 or 3 or 4 or 5. For that, you need to know chromatography. Identify structure of an unknown compound. If you cannot see the molecule by using spectroscopy, you're not a chemist. This is alchemy was. The Muslims have invented this new science. And that requires spectroscopy. Right? Third, you have to modify the structure. And that requires synthetic chemistry. So you need to know chromatography, you need to know spectroscopy, and you need to know medicinal chemistry or derivatization. Only then you are a chemist. Yes, sir.
So, I want to ask if there are two protons on the ring in space, can they cause splitting on each other?
No. If they are in space, they would not cause splitting. They can only affect because they're not. You remember that splitting is not because is not because. Do you really know that splitting of germinal or basinal protons are not because of their proximity? This is actually through bond the information is transferred. Okay? Here, no such bond exists. There's only two of them closer to each other. That's called diamond. No. So between this and this, you have two options. How would you do that? You have no other technique except annealing. So what you would do, classical annealing one-dimensional steady state, you saturate one of them, like methyl, and you see the effect on this. It means that they are up, and this is endo. If you don't see this effect, it means they're exo, because they're so far away from each other. This proton and this proton, so far away. Okay? Isn't it beautiful? Yes, madam.
Once if I remember correctly, absence of family means nothing. It means that if it is the saturation could be immediately transferred to another. If I remember correctly, you were giving an example of a football match. Taking picture, then of each.
What a wisdom! I just so honestly, I sometimes feel that the intellectual height of people are so. Okay, she's actually asking a very important question because I often say this: the absence of memory means nothing. Here I keep repeating it that if there is no memory, it means they are not close to each other. The reason why I said that because if your experiment is not properly designed, if your experiment in your sample you have dissolved oxygen, you have undissolved particles, you don't see any relaxation. It's a competing relaxation. There are 4 relaxations competing with W2. This is forbidden relaxation. And if you give them a sink to throw the energy, nothing would appear. And it doesn't mean they're not close to each other. It means that your experiment hasn't been not been very good. So it means that whenever you see an absence of NOE, when there is a presence of NOE, good, no problem. When there is an absence of NOE, rethink. check whether your experiment is bad, whether this has been recorded not correctly. Thank you for asking this. Any other question? And this is the time to say farewell, and I feel extremely sad, and I don't know what to do.
We have another class for this.
You want?
Yeah.
1-to-1.
No, is he?
Who is he?
No, it is the same.
You're not satisfied? Another class, okay. No? Meena doesn't go there. Okay, anyway, you're always welcome to come and discuss. And of course, we have this wonderful occasion of you coming to Islamabad, all of you.
Just 3 days enough.
Oh, no. Okay, so what should we do? 1 year course? Okay, so yes,
Related with DNA, like NMR.
I have no idea about DNA. I know very little about DNA. My knowledge about DNA is just so superficial. I just only know that DNA is present in me. That's the only knowledge I have. But you know, the applications can be different. Yeah, DNAs and RNAs, they all have protons, and people use it. And especially DNAs, the helical structure, NO is very important. NO is just a key technique for modern connectivity. Secondary structure, tertiary structure, quaternary structure, proteins, DNA, and all. This folding is what is only determined by NO. There's no other technique you can get folded. Of course, you have a crystal, you can do that also. But NMR is the only technique through which you can, that this long chain has folded over like this, or is a globular protein, or is a linear protein, or whatever. So anyway, similarly with RNAs and DNAs too, because they have helical structures. Okay. Any other question? You've been absolutely superb. I must say that I've been so pleased to have you all. It enriched me. I learned a lot, and I didn't really, unfortunately, got much time to interact with you. My travel was very frequent, so it was regular classes I was missing. For that, I apologize, but I thank you. Thank you. Thank you.
And this is the award that sir received last night in Lahore. This is the Shahid Fazlur Muhammad Saeed Award. How would you Small amount.